Naloxone, a life-saving drug. Presentation by Kimberly Armstrong, Issa Johnson, and Cassie Farber. First, let's start off with some background information. The common name of our drug is naloxone. The IUPAC name is 1-N-allele-7,8-dihydro-14-hydroxynormorphinone. Brand names include Narcan, a nasal spray, and Evzio, an autoinjector. More specific information will be discussed on the next slide. Naloxone is a high-affinity opioid antagonist. It was approved by the FDA in 1971 to quickly treat opioid overdoses. There are 3 ways to administer naloxone: through a syringe, through an auto-injecting device, much like the EpiPen devices, or as a nasal spray. Naloxone is not addictive and is instead used to counteract the effects of other addictive drugs, specifically opioids. It works to reverse opioid overdose in the body for about 30 to 90 minutes, meaning that the person may still end up experiencing the effects of the overdose after naloxone wears off. However, naloxone has no effect on someone who does not have opioids in their system. Naloxone is mostly used by emergency personnel, such as policemen or EMTs, but it is available for purchase at most pharmacies for family and community members. It is also possible to get naloxone from community-based distribution programs, local public health groups, or local health departments.
So now we're going to talk about the mechanism of action. The brain contains 3 types of opioid receptors, delta, mu, and kappa. Naloxone is non-selective, meaning that it can bind to all of the opioid receptor types. Upon entering the body, naloxone travels to the brain, meaning it is able to permeate the blood-brain barrier, and inhibits the intake of opioids into the body by docking on the delta, mu, and kappa receptors. Naloxone has a stronger affinity to the opioid receptors, so it is able to knock the opioids off the receptors for a short time. While the naloxone is docked, opioids are prevented from binding to these receptors, thus curbing the effects of the overdose. Naloxone may cause the induction of an acute withdrawal syndrome since it is so fast-acting, or pulmonary edemas and cardiac arrhythmias when used in high doses for patients that are being treated for pain with an opioid. Although there are possibilities of negative side effects, the administration of naloxone can quickly restore normal breathing if their breathing has slowed or stopped. Now let's get into the synthesis of naloxone.
In the first step of the reaction on the starting material oxymorphone, the alcohol on the phenyl group is protected to prevent it from reacting with the reagents in later steps. To do this, the starting material oxymorphone is reacted with acetic anhydride in the presence of bases D-MAP and triethylamine. This converts the alcohol into an ester, thus protecting the alcohol group. In the second step of the synthesis, the product from step 1 is reacted with MCPBA, a known oxidizing agent. The lone pair on the nitrogen reacts with the MCPBA and steals an oxygen atom. This then gives the nitrogen a positive charge while the oxygen has a negative charge. This allows for nitrogen to react in the next step. In this step, the charged atom of the starting material reacts with the Burgess reagent. The overall result of this step is the charged oxygen atom is removed while the oxygen atom of the alcohol binds to the methyl group attached to the nitrogen. We will talk more in depth about the Burgess reagent and how it works in the next couple of slides.
Let's go into a little more depth with the Burgess reagent. In this part of the synthesis, the negatively charged oxygen atom attacks the sulfur of the Burgess reagent, and the triethyl nitrogen is kicked off of the molecule. The other nitrogen of the Burgess reagent then grabs one of the hydrogens from the methyl coming off of the nitrogen on our molecule, which kicks off the oxygen on the sulfur. This creates the nitrogen double bonded to the carbon we see as the product of this reaction. Later in the reaction, the oxygen atom attacks the carbon on the double bond, making it positive. The negative oxygen that was created in the Burgess reagent in an earlier step deprotonates this positive oxygen, making the OCN bond. In this next step, the ketone is protected in a very simple mechanism by reacting it with the methanol to prevent it from reacting later on in the next step. This creates 2 ether groups where the ketone used to be.
Step 5 of the reaction has two parts. First, the nitrogen in the CH2 group of the starting material is put through a Grignard reaction to attach the alkene to the end of that chain. This also converts the oxygen back to an alcohol by taking a hydrogen from the solvent THF. THF then deprotects the original alcohol on the phenyl group. We will examine the Grignard reaction in greater detail in the next slide. Here we have the Grignard reaction mechanism. In this mechanism, a resonance structure exists between the nitrogen, carbon, and oxygen, making a double bond on the nitrogen and a negative charge on the oxygen. This allows for a great opportunity to use a Grignard reaction to attack the double bond, kicking the electrons back to the nitrogen atom, making the nitrogen neutral. This makes the R group on the nitrogen vinyl. The oxygen then grabs a hydrogen from workup, making the alcohol again. The final step of the synthesis, step 6, includes reacting the starting material with HCl in the presence of THF in order to deprotect the ketone. After this is completed, we have the final product of naloxone.
When the R group coming off the nitrogen is vinyl, the final product is naloxone. But what if the R group was something else? Would it affect the body differently? This leads us into the conversation of other possible derivatives for this specific synthesis. When the R group is cyclopropyl, the product becomes naltrexone. Naltrexone binds and blocks opioid receptors much like naloxone, but it is reported to reduce opioid cravings. This is meant to be taken more as a preventative measure rather than an emergency situation after an overdose has already occurred. Furthermore, when the R group is cytolbutyl, the product becomes nalbuphone. The structure of nalbuphone is virtually useless in the body, but with an OH group in place of the ketone, you can create another opioid called nalbuphine. Nalbuphine acts as an agonist at kappa opioid receptors and an antagonist or partial agonist at mu opioid receptors. Nalbuphine is the only opioid pain medication that is not a controlled substance in the United States. Crazy to think what one little difference on a chemical structure can make. Here are some of the sources that we used. If you have any thoughtful questions, feel free to ask our group so that we can all get participation points for this project. Thank you for listening. We hope you're all staying healthy and safe. Go wash your hands.